topic. Today's topic is staff seminar. In this one, we have planned to discuss two published international journal papers. The first one is ballistic performance of high-strength low-alloy steel weldments. The second one is deformation and failure mechanisms in ASI 1310 steel under ballistic impact. If time permits, we will discuss both the papers. Otherwise, we will wind up with one paper discussion. And the first paper discusses about the ballistic performance of armed steel wells. The paper was authored by Maksud Reddy and Mohandas. The paper was published in the Journal of Materials Processing and Technology in the year 1996. The objective of this paper is to identify the adjacent softening phenomena with respect to the GMAW welding process with various heat input conditions. And the properties were correlated with the microstructural and micro-hardness survey. For this investigation, they were taken into 12 mm thickness HSLA steel plates, and it was heat-treated, that is quenched and tempered, and the welds were performed with austenitic stainless steel fillers. Normally, the quenched and tempered steel welds are welded with austenitic stainless steel filler because the base material offers very high strength of about 1300 megapascal. It has to be welded with quite toughness weldment. That is the reason these are welded with austenitic stainless steel fillers, and all welding was performed using GMAW process. And the table shows the chemical composition of your base material, and the figure shows the testing arrangement, that is weld metal arrangement. That in this one, fired with with 300 mm plate was cut into singly bevel hook, and it was welded with GMAW process with three different heat input conditions. That are, in that one, the filler wire is austenitic stainless steel filler, the welding current 250 amps and arc voltage 28 volt was maintained, and it was welded with preheat temperature of 150 to 170 degrees Celsius. Here the varying parameter is the welding speed. Within that, the heat input is achieved between 0.6 kJ per mm and 1.2 kJ per mm and 1.8 kJ per mm. This is the ballistic testing arrangement. The arrangement is available in Defense Metallurgical Research Laboratory, Hyderabad. The fabricated target is placed 10 meters apart from the gun muzzle, and in between 6 meter and 8 meter, there is two velocity probes are available, which is used to measure the travel velocity of the projectile for ballistic testing. And for this investigation, they have used 7.62 armor piercing incendiary. The details are available here, which is made up of point steel. And coming to the research point, the hardness measurement were done across the weld metal. Across the weld metal, the hardness was measured, and it was plotted as a graph. Within the graph, we can able to identify, and these graphs for three different heat input conditions. This graph belongs to 0.6 kJ per mm. In that one, this graph belongs to 1.2 kJ per mm. Both the graphs are looks similar, but there is a small difference in between these two graphs. That is, at the weld metal location, this is the weld metal location, the hardness is between 280 because where it is measured at 30 Newton load. Both conditions, the hardness at weld metal is same. But apart from the hard metal, in the pre-temperature zone, we can able to see there is a difference in soft zone width. So this is your soft zone. In the pre-temperature, actually, if you didn't weld, your hardness profile will be a horizontal one, which is closely equal to 600 Mech. But if it is welded with austenitic stainless steel filler. That is the reason it shows very low hardness in the weld metal region, that is middle region. And apart from that, if you look upon the base metal region, it is again getting increased. But in between your weld metal and your heat affected zone, there is a soft zone. Low hardness zone is prevailing. This is the problem which is addressed in this paper. But again, when you compare these two graphs, there is a width difference. In this one, low heat input conditions, the width of the soft zone is smaller compared with the higher heat input of 1.0 kJ per mm. If you still increase the heat input of about 1.8 kJ, you can able to And from the ballistic test results, they came to know that at the well metal location, it offers no resistance for the bullet penetration. The bullet is completely fast proof. And in the base metal location, they observed a shatter, that is, bullet is bounced back and it is disintegrated into many parts, that is called the nominal shatter. And in the heat affected zone, they were observed two different zones were identified with the same kind of plug and ejected. That is, a soft plug is ejected at the rear side, and when it is at complete well metal, it is called punching or nesting kind of failure was observed. We discussed why this kind of failures were achieved. So with respect to hardness, actually this kind of base metals are quenched and tempered. When the material is quenched and tempered, it consists of martensitic microstructure. That is the reason these kind of base metals offer very high strength in unwelded conditions. But that martensitic structure is quenched and tempered martensitic structure is welded again. And in the heat affected zone, there is a possibility of again tempering of the already tempered material. And also in the near well zone, that is near your fusel zone, it goes very longer time for cooling. That is called your normalizing kind or annealing kind of treatment. That is the reason we can able to achieve a different hardness profile starting from your well metal towards your base metal. That is the reason high hardness zone in the HSZ and low hardness zone also prevailing in the HSZ zone alone. And that could be achieved by the various hardness in the base metal, and if the heat input also plays a vital role. If the heat input is high, then the base material, that is your heat affected zone, need quite longer time to cool the base material. If the heat input is very low, then the time required to cool the base material, that is your heat affected zone, is very less. That is the reason you can able to achieve different kind of results. And also, narrow heat affected zone expected to be restrained from the deformation and exhibit better ballistic resistance. If we are really looking for a better ballistic resistance, then your soft zone width shall be as minimum as possible. So when we really looking for better ballistic resistance, your heat input has to be controlled with minimum heat input. And the wider soft zone, which offers wider soft zone means the heat input is higher in 1.8 kJ per mm. That kind of heat input only, the width of the soft zone is wider. So wide means it may be beyond the 7 mm. That is why the 7.62 APA is passing through, plugging kind of a failure. And intermediate heat input, that is 1 kJ per mm, such cases your intermediate ballistic resistance is achieved. And coming to the well metal alone, if we consider the well metal alone, that is austenitic stainless steel well metal, with respect to different kind of heat input, it offers different kind of microstructure. Though the well metal is austenitic stainless steel well metal, we know very well the austenitic stainless steel well metal definitely offers a delta ferrite at the grain boundary with massive austenitic structure. But it is again changed, the morphology is again changed with respect to the heat input what we are supplying. Basically, these three kind of microstructure in well metal alone was observed. That is vermicular ferrite. Delta ferrite is not only available in the grain boundary, vermicular and acicular delta ferrite and the lazy delta ferrite and skeletal delta ferrite. These four different kind of morphology was observed in this kind of well metal with respect to various three different kind of heat input conditions. And coming to the post-grained HSZ zone, we know that very well where we can able to have post-grained HSZ. Very much nearer to your fusion line, where only the temperature profile goes very higher temperature. Next to your well metal, where we can have the higher temperature. So in that region, the grain portioning is normally achievable. And coming to next zone, that is apart from the fusion line, if you move around, move apart, where you can have the temperature profile is the maximum peak temperature achievable is very minimum. That is the reason in those regions it offers fine-grained microstructure. Coming to the base metal, it is a tempered acicular martensitic structure as we discussed earlier. And with respect to the schematic of hardness distribution in relation to the microstructure in the HSZ or HSZ steel well deposit, when the material is welded with low energy, low heat input, the width of the subzone is very minimum and if it is welded with high energy, high heat input conditions, the width of the subzone is wider. And this can be again correlated with your iron carbide equilibrium diagram. So in your well metal, if it is available next to the fusion zone, the point located in D, where it offers higher temperature next to your fusion line, that is the peak temperature is higher. That is the reason it offers a grain coarsening kind of structure. Whereas coming to the next point, see, here we have a intercritical temperature region, where your material will undergo different kind of microstructural transformation. That is this region C, where you have temperature is between 727, above 727, that is above A3, and but below your high temperature line. And also coming to the point B, here it is just lying on the same A1 line, and that is your lower critical temperature line. And if you consider the point A, your temperature is very below the critical temperature, where you may not expect any kind of phase transformation. All the material, what is the microstructure available at room conditions will withstand up to that temperature. So this is how the microstructure changes occur in the fusion zone to your heat affected zone, complete heat affected zone. The heat input increases, your acyclarity decreases. So normally people used to say when we are looking for acyclar kind of morphology, acyclar structure is a basket wheel structure. When we wheel the basket like this, your grains will interlocking kind of structure. If we have a high strength, like if we have the structure like this interlocking structure, it can offer very high strength and very high hardness. If we are really looking for acyclar morphology, then we have to control the heat input into low level. That is the reason acyclar morphology. If the heat input increases, the grain will not form like a basket wheel structure. Instead, it forms a coarse grain structure of different kind of morphology as what we have discussed previously. And microstructure again depends on chemistry and well thermal cycle. Well thermal cycle is perfectly belongs to your heat input conditions what we are maintaining. And region near to fusion zone, that is what we have discussed with the aid of your iron carbide equilibrium diagram also. Near zone, the temperature is above A3, well above A3, and fast cooling rates, coarse grain structure is definitely formation of very high coarser structure of modern side. That is the reason the hardness graph shows next to your well metal higher hardness zone. And heat input increases, longer cooling time, excessive grain growth, and coarse transfer of microstructure is observed. And region away from fusion zone, when we look apart away from the fusion zone, the temperature, peak temperature is just above A3. So we can expect, instead of martensitic structure, we can expect ferrite plus high carbon austenite, and finally it will most convert as a martensite if the base metal is continuously cooled to room temperature. And even martensite again can be converted into ferrite plus Fe3C if it attains a room temperature, that is called ambient temperature. That is the reason in the region apart from the well zone, the peak temperature is just above A3. The point, see what we have discussed with the aid of your iron carbide equilibrium diagram. So final microstructure is ferrite plus iron carbide. That is again we can say the combination of ferrite plus iron carbide is, you can say usually perlite. Instead of martensitic structure in the base metal, it is converted into perlitic structure during welding, but it is not unintentionally it is converted as perlite. That is the reason it shows very soft zone in between your base material and in the heat affected zone. And that zone definitely offers very low poor ballistic resistance. That is the reason it passes the bullet to pierce through. And which is again compared with the different region what we have just discussed. In the region C, it is your unaffected base metal, and region A have very low hardness. If we really looking for a better ballistic resistance, the hardness should be at least 600. Actually, when it is measured with 30 Newton load. And you see, in the well metal, hardness is 200. That is the reason it allows the bullet to pass through. And in base metal, this is the base metal zone. Apart from this region, it is the base metal, unaffected base metal. There also offers high penetration resistance, that is called your bullet shattering. and in location B, we have very low hardness profile, which is again compared with your well metal zone, it offers higher hardness zone, but it does not work when it is ballistically evaluated. That is the reason this region and region B is completely allow the bullet to pass through. And from their study with 3 different heat input conditions and the width of the soft zone, they have measured now. With that, they have concluded an empirical relationship. That relationship is drawn between the penetrator diameter and the soft zone width. This is your width of the soft zone. If the heat input is low, the width of the soft zone is very less, that is 0.62 mm, 1.25 mm and 1.87 mm. And also the penetrator diameter is 7.62 APA, what we have been discussed already. And there is a ratio between D and W, that is diameter with respect to the width of the soft zone. So when low heat input is achieved, the ratio between the D to W is 0.26. And similarly, the heat input increases, the ratio is getting increases. The heat input again further increases, the ratio is getting increased. So if we really looking for good ballistic resistance, the ratio between the diameter and width of the soft zone shall be as minimum as possible. Then only we can able to say good ballistic performance can be achievable. If it is continuously increased, the intermediate performance in between these two, and if the heat input increases and also if parallelly increases the ratio, poor ballistic resistance, that is through penetration is witnessed in the photographs also. And the empirical relationship says that ballistic performance and the ratio of width to diameter decreases, your ballistic performance increases. Summary: this welding of precision tempered steel in a heat treated conditions definitely alters the microstructure near to the fusion zone. This is unavoidable. It is very clear. And this microstructural alteration definitely lowers the yield strength, parallelly ultimate tensile strength, and the point where the welded plates do not possess the required ballistic resistance, that is properties, and specialized welding procedures such as backing up of the soft region with hard plates or control of heat input by therefore we can have a necessary overcoming methods to overcome this kind of difficulties. From this investigation, they have concluded that adjacent softening is observed. The width of the soft zone is proportional to the heat input. Greater the heat input, wider the soft zone. And softening can be due to the heating of the base metal in the intercritical region and subcritical regions, which results in microstructure which is other than the base metal microstructure of fully marble structure. Better ballistic resistance, if it is necessary to limit the heat input in the weld to reduce the width of the soft zone. An empirical relationship between the width of the soft zone and protected diameter is proposed to serve as a guide for ballistic performance. Can I continue? If you have any queries, please. Any cooling method is possible to reduce the... Definitely the